I'm going to do this example where you're going to be looking at scalar multiplication as well as addition and subtraction, and sometimes all in the same problem. Can you do that? Can you do scalar multiplication with addition and subtraction all in the same problem? Sure, it's totally legal. So let's look at some examples with actual numbers. So hopefully this will clear up any confusion you still might have regarding anything we just covered. So in this example, they're giving us two lovely vectors in component form. Yay. And we're going to find the following and write our results in component form, because our results are also going to be a vector. So letter A, 2/3 u. This is scalar multiplication right here. This is an example where we're multiplying u with the scalar. Scalar is a pure number, 2/3. So how do we do that? Very carefully. I'll do an intermediate step. You're going to take 2/3 and multiply it with this vector. And you can kind of think of the 2/3 as distributing. So you're going to have 2/3 times -3 and 2/3 times -8. And then clean these up. I mean, just do a little bit of reducing if it's able to be reduced to lowest terms. So the first one after reducing, we get -2. And the second term there, can't really reduce it. So it's just going to be -16/3. And I prefer improper fractions rather than decimals. So unless I start doing a problem with decimals, don't give me decimals. That's sort of an unwritten rule in my class, but I'm telling you in advance. So please write it as -16/3 and not like -5 point whatever. Okay, that's scalar multiplication. Now visually what happened, if you were to graph the u vector, you would simply find -3 on the x-axis and -8 on the y-axis, and then find the point -3, 8, and then draw this vector in standard position. There's u. And the new vector, which occurred when we multiplied u with 2/3, if you graph -2 and -16/3, you find the x coordinate is -2 and you find the y coordinate -16/3. I claim it would be pointing in the same direction as u, but it would be about, it's 2/3 in magnitude, 2/3 of the length. And that's it. That's scalar multiplication. Does that help?
Yes, it does.
Great. Okay, in letter B, they're doing some subtraction. Woo! Let's do it in slow motion. First, you're going to take the vector v, which in component form is angular brackets 8, 25, and you'll subtract the other vector u with components -3 and -8, and you're going to get a vector. So I'm going to leave some room here. You're simply going to take the difference of the x components, so 8 minus a -3, comma, 25 minus a -8, and then do the arithmetic. So your final answer looks like it's going to be 11 and 33. Boom, and we're done. So there is the result of scalar, or excuse me, vector subtraction. It's going to be a vector. And now letter C involves scalar multiplication as well as vector addition. And you want to do the scalar multiplication first, followed by the vector addition. So let's just go through this quickly to see if you are on task. Just like in math, regular algebra, PEMDAS, multiplication always comes before addition. So you definitely want to do the scalar multiplication first. So if I did this in slow motion, and I'm going to do it in really slow motion, you're going to have 2 multiplied by angular brackets, -3, -8, plus 5 angular brackets, 8, 25, like that. And I'm running out of room here. Oops. Then you're going to distribute the scalar. So you're going to have like 2 times -3, and I'll just do the multiplication quickly here. So the scalar multiple there of 2 with the u is going to be that vector with -6 and -16 as components. And then when I distribute this 5, woo, I'm going to get 40. Oh, crap. What's 5 times 25? 125. Okay. So that's an intermediate step. And now when you sum up 2 vectors, you're going to get a vector. So I'm going to put my angular brackets, and then I add the x components together, and then a comma, and then I add the y components together, and then I finish by actually doing arithmetic, which sometimes I can screw up with if I'm not careful, and that's why I encourage you to use a calculator to triple check yourself. And there's your final answer. Did everybody get that?
Yeah.
Yay! Success! Well, congratulations to all if you did get it. If you didn't get it, don't be too hard on yourself. You're just learning how to do vectors. Okay? Okay, this is a typical problem you'd see in a linear algebra class, but I think it's important enough where this will be on quiz 1, but I will change the numbers. Okay, I'm telling you, well, and the previous problem is going to be on quiz 1 also, so know how to do that, the A, B, and C. So how does this operate here? They're giving you a vector W. They're giving it to you. Like, there's W. Okay, fine. And you already know what U and V are because they gave you U and V already. Okay, so you know all 3 vectors. So what do they want? They want you to find 2 scalars, pure numbers, A and B, such that you can write W as a linear combination of the vectors U and V. What the heck does that even mean? It means that W can be written as some pure number A times U plus some other pure number B times V. So what do they want? The final answer, once we're done, is you have to say what is A and what is B. Those are the mystery numbers. So find the mystery numbers. Now, when I say that this kind of thing is done in linear algebra all the time, when I teach linear algebra, I'm not teaching it this semester, this is something I ask my students to do all the time. So I'm giving you a leg up in your linear algebra class. So writing a vector as a linear combination of other vectors. Okay, so what? So I'm going to do the intermediate step here, all the intermediate steps. So when they say W is equal to AU plus BV, I'm going to just fill in what I know. I know that W in component form is that. I don't know what A is. It's a mystery, but I do know it is a pure number. I just don't know what the pure number is. Oops. And then B is some scalar, pure number. I don't know what he is either. So this is an intermediate step. So just go with me because this will make sense. You have all the tools to do this problem. You do. Because when you solve a linear system, which is what's going to happen here shortly, you learn how to solve linear systems in your algebra class like 2 years ago. Okay, I'm going to do the scalar multiplication because I'm supposed to. So let's do that. That's our next step. So this, when I distribute the A, the first component will be -3 times A, comma. The second component, -8 times A. And then when I distribute my B scalar, I'll have 8B, comma, 25B. Well, now what? Don't worry, we got to go slow here. Let's add the right-hand side vectors together because that has to be a single big old vector. So the x component will simply be the sum of the x components of the vector here, comma, and the y component will be the sum of the y components. And the left-hand side hasn't changed. I'm just going to copy it down. Okay, now, this is the key. Remember when I said equality of vectors, even though it seems very, very obvious, is going to save us on occasion? It is now going to save us. We need it. Well, how is it going to be helping us? Well, I claim we have an equation where one vector on the left-hand side, it has to be equal to the vector on the right-hand side. This vector has to equal this vector. So by equality of vectors, what needs to be true? What needs to be true is the 14, that component has to be the same as the x component of the right-hand side vector, -3a plus 8b. And similarly, the 41 had better be equal to -8a plus 25b. And folks, this is a linear system of equations. There's 2 equations and 2 unknowns. And you learned how to solve this in an algebra class. Now, there's different ways to solve it, of course. One way would be to use the substitution method. That would work. I'm going to use the elimination method. So if you don't mind, I'm going to multiply the top equation by both sides by 8. Okay. And I'm going to multiply the bottom equation by, because I want to add these two guys together is what my plan is. I'm going to multiply the bottom by -3, both sides. So 8 times 14 is what? 112. And then when I have 8 over here, I've got -24a plus 64b. Yeah, I can't talk right now. Sorry. Don't know. Can't. I did not tell me.
I don't know what kind of fruit it was.
Okay. And then what? I think, did I do all that multiplication right? Stop me if you see me do a mistake, okay? Speak up. So what is 112 minus 123? Quick. -11. Here I get 0. What's 64 minus 75? Quick. -11b. This will be easy to get b. b is going to be just -11 over -11, right? Everybody with me? So what does that mean? B is equal to 1. I got one of the unknowns. Now what? Well, I need to get another unknown. How about if we substitute b equals 1 into this equation or the original? How about if I do the original where it's -3a plus 8b equals 14? If I substitute b equals 1 in this original equation here, I should be able to get the a, right? What if I subtract 6 from both sides, and then a is equal to -2. So final answer, a is -2 and b is 1. And those are the mystery scalars that will enable us to write w as a linear combination of the other two vectors, u and v. So what has to be true right now? W has to be -2 times the u vector plus 1, that's the b, times the v vector. This has to be true. And it is. You can double check it. Okay? So this was a multi-step problem that took a little longer than 2 minutes to solve, but it uses all of your knowledge that we just went over. Vector addition, scalar multiplication, and then solving a system of 2 equations and 2 unknowns from your algebra days, okay? So let's do a theorem of properties of vector operations, and then we'll wrap this up for today. And on Wednesday, we'll pick up learning how to unitize a vector, writing a vector as a standard with the standard unit vectors, and more, okay? So we'll be resolving a vector into its components next time too. Okay, fun stuff. So this theorem is just more obvious things. You may think it's pretty obvious. Although if you go take a vector calculus class, they might make you prove these. Just so you know. So suppose somebody give you vectors in the plane. That means 2D. And by the way, this theorem will work in 3D also. And let's say C and D are just numbers. They're scalars. So what's true? Well, it doesn't matter what order you add 2 vectors, because you'll still get the same result. Now, that's not true for subtraction. Subtraction order does matter. Just like with numbers, 5 minus 2 is not equal to 2 minus 5. But 5 plus 2 is equal to 2 plus 5. So you have commutativity as long as you're adding. Fine. What if you have 3 vectors and you're trying to add them together? Well, you could add the u and v together and then w, and that'd be fine. Or if you prefer, you could add the v and the w together and then add u. Either way, it doesn't matter. Same thing, because we have associativity. What about the 0 vector? If you add him to any vector, it's just like adding the number 0, you'll still just get the vector. What if you take a vector and add his opposite? You'll get the 0 vector. And make sure you put a little arrow on top, because if the answer is 0 with a vector on, it's a 0 vector, but you just write 0 on your paper, I'm going to have to take away a point or more for bad notation, because the pure number 0 is very different from vector 0. Okay, what if you have two scalars that you're trying to multiply a vector with? And you want to first do one scalar and then hit it with the other? Fine. Or you can multiply the two scalars together and then multiply it with the vector. It doesn't matter. What if you have the sum of two scalars that you're multiplying with a vector? You could do it like that. That'll work. Or you can distribute if it helps make the problem easier. Legal. Similarly, you can distribute a scalar over the sum if that makes it easier. Or you could just add the vectors together first and then hit it with the scalar multiplication. If the scalar is 1 and you're doing scalar multiplication, well, 1 times anything is just the anything. That's the multiplicative identity. And 0 times a vector will be the 0 vector. So if your scalar multiplication involves the number 0, then you'll always just get the 0 vector. Not very interesting. Okay. Woo! And